Welcome to ElectrAspirant, an assistance to electrical students for objective type exam preparation. It's an initiative of Department of Electrical and Electronics Engineering, Christ College of Engineering, Irinjalakuda. In this presentation, I would like to discuss some numerical problems in the topic frequency domain analysis under the subject control system. The prerequisites we need is as shown. Coming to the first question, the board plot of a transfer function g of s is shown below, and it is given that the gain at different locations it is minus 8 dB and 32 dB at 10 rad per seconds and 1 rad per seconds respectively. The phase is negative for all omega. We need to find the transfer function. Now, as per the given magnitude plot, we have only one line segment. We have only one line segment is shown, that is it is starting from with a negative slope. Okay, and it is shown for a 1 decade, that is at 1 rad per second the gain is 32 dB. At 10 rad per second the gain is minus 8 dB, so that we can find the slope of the line. It becomes minus 40 dB per decade. Okay, since it is a going downward direction, so the slope is minus 40 dB per decade, which indicates the presence of a term s square in the denominator of the transfer function. So the transfer function has the form k divided by s square. From the by the observation of the board magnitude plot, it is clear that the transfer function having the form k by s square. Now we need to find the value of k. For that, at 1 rad per second, the gain contributed by the gain contributed by the constant term only. So we can find the value of gain k. That is by equating 20 log k. By equating 20 log k with 32 dB, we will get the value as k equal to 39.8. Hence, the answer become option B, that is 39.8 divided by s square. Now coming to the next question, the open loop transfer function of a unity feedback control system is given. It is g of s equal to a s plus 1 divided by s square. Now we need to find the value of a such that the phase margin is 45 degree. Okay, so when we have the problem under the phase margin or gain margin like that, we need to refresh the expressions of those frequency domain specifications. Here g of s equal to a s plus 1 by s square. Now we can find the sinusoidal transfer function like this, that is g of j omega equal to 1 plus j a omega divided by j omega the whole square, and we can make the magnitude part and angle part like this. Okay, now we know the phase margin, it is defined as gamma equal to 180 degree plus 5 gc, where 5 gc it is the angle at which omega equal to omega gc, and to get the phase margin as 45 degree, the 5 gc should be minus 135 degree. Now by equating this relation, we can arrive a relation that tan inverse a omega equal to 45 degree, or in other words we can find omega equal to 1 by a. Okay, so we have a relation between a and omega. Now we know to find the gain crossover frequency, that is it is nothing but when the magnitude equal to unity, the corresponding frequency is named as gain crossover frequency. Now from this equation, that is magnitude part when equated with 1, we can make a another expression, that is omega raised to 4 plus omega raised to 4 equal to 1 plus a square omega square. Now by substituting this relationship there, we can find the value of a as 0.841. That is answer becomes C. Now coming to the next question, A system with zero initial conditions has the closed loop transfer function T of s equal to s square plus 4 divided by s plus 1 into s plus 4. The system output is 0 at the frequency. Okay. So uh, by making the sinusoidal transfer function, we can form that is its magnitude part only. It becomes magnitude of t of j omega equal to 4 minus omega square divided by root of 1 plus omega square into root of 4 square plus omega square. Now we need to find the system output is 0 at the frequency. Okay, now the magnitude becomes 0. By the observation of the expression, it is very clear that when omega equal to 2 rad per second, the system output becomes 0. Okay, so the answer is C, option C. Okay, now coming to the next question. The gain margin of a unity feedback control system with the open loop transfer function G of s equal to s plus 1 divided by s square is. Okay, here also first we need to make the given open loop transfer function in sinusoidal transfer function. So it becomes g of j omega equal to 1 plus j omega divided by j omega the whole square, and we can make the corresponding magnitude part and angle part. Okay, now we need to find the gain margin. We know the gain margin, it is defined as 20 log 1 by the open loop transfer function at omega equal to omega pc, where omega pc is the phase crossover frequency. It is nothing but when the angle become minus 180 degree, the corresponding frequency is phase crossover frequency. Now by equating the angle expression with the minus 180 degree, we can find the phase crossover frequency, and it becomes 0. That is when omega equal to 0, it happens. Now by substituting for omega equal to 0 in the reciprocal of the magnitude of g of j omega, it becomes 0. Hence the gain margin becomes 20 log 0, which is a not defined value. Then hence the answer is D. Now coming to the next question. For a transfer function g of s equal to 5 into s plus 4 divided by s into s plus 0.25 into s square plus 4s plus 25. The values of the constant gain time and highest corner frequency of the board plot respectively are. Okay, so it is the question related to corner frequency and to get the constant gain time. Okay, for that we know, since the given transfer function, it is given in the pole zero form. Now first we need to make the given transfer function in time constant form. That is, we need to make the constant portion. Okay, that is we need to the constant portions. That is these portions should be unity. That is, we need to take 4 from the numerator, and from the denominator, from this term we need to take 0.25 outside, and from this term we need to take 25 outside. Okay, so by making the time constant form, we have, it becomes g of s becomes like this. Okay, g of s become like this, and we can get the constant time directly as 3.2. And we know the corner frequencies, they are the reciprocal of the coefficients of s terms. So this term having the corner frequency is 4 rad per second. For this term it having the corner frequency 0.25 rad per second, and for this term having the corner frequency 5 rad per second. So the highest corner frequency is 5 rad per second. Hence the option become A. Now the next question, that is the frequency response of a linear system g of j omega is given below. The gain margin and phase margin are. Okay, so again we have we should know the concepts of gain margin and phase margin. The gain margin, it is nothing but 20 log 1 by magnitude of open loop transfer function at omega equal to omega pc, and phase margin, that is gamma equal to 180 degree plus 5gc, where 5gc it is the angle of the open loop transfer function at omega equal to omega gc. Okay, that is omega, where omega gc is the gain crossover frequency. Now from the table it is clear that that is at a when the magnitude become 1, that is the corresponding to our gain crossover frequency, and at that time the angle is given as a minus 18 minus 150 degree, that is phi gc equal to minus 150 degree. Hence the phase margin gamma equal to 180 degree minus 150 degree, so it becomes 30 degree. Okay, so the phase margin is 30 degree. Now to get to the gain margin, that is, we know the gain margin, it happens at the phase crossover frequency, that is when the angle become minus 180 degree, it is in the corresponding phase crossover frequency. Then the corresponding gain, it is given as 0.5. Okay, the corresponding gain is 0.5 here. Now we need to find the gain margin as per the expression 20 log 1 by 0.5, so it becomes 6 dB. Hence the answer is A, option A. Now the next question, it is if compensated system shown in figure has a phase margin of 60 degree at the crossover frequency 1 rad per second, then the value of gain K. Here also first we can find the open loop transfer function by multiplying these two. We get the open loop transfer function as K plus 0.366 S into 1 divided by S into S plus 1. That will be our open loop transfer function. Then we need to make the transfer function in sinusoidal form. Then by using the data phase margin, that is gamma equal to 60 degree, that is gamma, we know gamma equal to 180 degree plus 5 gc. From that we can find the value of 5 gc there, and it is given at the gain crossover frequency is 1 rad per second. By using those relations, we are able to find the option answer C. Yes. Okay, now the next question. In the GHS plane, the Nyquist plot of the loop transfer function g of s h of s equal to pi into e raised to minus 0.25s divided by s passes through the negative real axis at the point. When the point passes through the, locus passes through the negative real axis, at that time the angle is equal to minus 180 degree. Okay, so first we can find the magnitude expression of magnitude and the angle expression of the corresponding open loop transfer function. Then by equating the angle part to minus 180 degree, we will able to find the corresponding value of omega. Then by substituting in the magnitude part, we will get the answer as option B, that is minus 0.5 comma j0. That will be the negative axis crossing point. Okay, now the next question. The Nyquist plot of a loop transfer function, it passes through minus 1 comma j0 in the g of s h of s plane. Then the phase margin, we know the phase margin gamma equal to 180 degree plus 5 gc. When the locus, when the plot passes through exactly through minus 1 comma j0 point, then the 5 gc, the angle 5 gc become minus 180 degree. Hence the gamma, it becomes 180 degree minus 180 degree, so the answer become option A. Okay, now the last question. We have a asymptotic approximation of a low magnitude versus frequency plot of a minimum phase system with the real poles, and 1 0 is shown figure. Now we need to find its transfer function. The first step is as per the given board plot, it is very clear that magnitude plot, it is very clear that there are 4 line segments, 1, 2, 3 and 4, which indicates there will be 4 terms, 4 s terms, then a constant term in the transfer function. Okay, so the first we can identify the corner frequencies. We can see the corner frequencies and the poles and zeros locations. So here initially the line starting from here, then at a 2 rad per second it have a deflection towards the right side or towards the negative direction in this direction. So we have the first corner frequency is 2, and since it is deflected negatively, that is a slope increased in negatively, we have the we have a term s plus 2 in the denominator. That is, we have the pole at s equal to minus 2. Now at a 5 rad per second, now the line deflected towards the positive direction. That is, now the slope just decreased to minus 40 dB per decade, which indicates the presence of 0, and it happens at s plus 5. The term becomes s plus 5, that it is on the numerator. Now at a 25 rad per second, again the line deflected to negatively, that is slope again increase to minus 60 dB per decade, which again indicates the presence of pole, and so we have the term s plus 25 on the denominator of the transfer function. Now initially you can see the slope is given as minus 40 dB per decade, and it goes like this. So it represents the indication of a double pole at the origin. So we have the term s square in the denominator. Now we need to find the constant gain k. For that, now we have the information of g of s as g of s equal to k into s plus 5 divided by s square into s plus 2 into s plus 25. Okay, now take form, make the g of s in time constant form. Thereby you can find another constant time as, say, k dash equal to 5 into k divided by 2 into 25. So we have the term k dash. Now find 20 log k dash, that is equated with the gain at 1 rad per second. The gain at 1 rad per second, it will be 14 dB, 14 decibel. Now equating with, you will get the value for k dash. Then by using that relation, we will able to find the value of capital K. It becomes 50. So the answer is D. Thank you for the listening. Thanks.